Okay, ladies and gents, welcome into this special video. I'm recording this on Sunday before finals week. I just wanted to do one example of buckling that we didn't have a chance to do in class. I did try to give you a little time in class to do your instructor evaluation, so please do that if you haven't done that already. I think the window on that's probably going to close tomorrow, so probably take care of that if you can, okay? I want to take time now to go through one buckling example, and I like this example because it kind of shows those things we talked about in class about how the boundary conditions can kind of affect what that effective length is to create that half sinusoid for buckling, and I think this sort of shows that and demonstrates that well. So this example is from the very last slide of the buckling lecture notes, so you can check that out there, or I've also recopied it here into the writing pad. So if you need to take a minute to copy this problem down, you can actually pause the video here now because we're not live at this point. So if you want to take a minute and copy this down, you can go ahead and do that. Otherwise, I'm just going to hop right into the problem. All right. So here we see an example where we have sort of the steel member that's in compression along the x direction, and it's relatively long member, 10 feet long. And it's supporting this axial load. Column has a 1x2-inch rectangular cross-section. Left end of the column is fixed. And it's kind of an interesting boundary condition that we have here. So this boundary on the left side is a little complicated. The left-hand boundary here, I think, is pretty easy to see that this is a fixed boundary. But the right-hand boundary is a little bit complicated. And the reason that it's complicated is because if this assembly, let's say, is going to bend about what is the z-axis, let's say it's going to buckle sort of in this fashion, then we would have what is a pinned fixed boundary. All right. So here about z-axis, we have a fixed pin. Okay. And you can see that if you thought about sort of this guy taking this half sinusoidal sort of shape in this general z direction, you would have fixed on this end and pinned on this end. Now, when it comes to buckling, you can buckle not just about one axis, you could also buckle about sort of the second axis. And in this case, we could have buckling about sort of this other direction, which would be a buckling about the y-axis, which if you're just kind of holding a ruler in your hand and not considering boundary conditions would be sort of the direction that you would expect it to bend in this situation, which would sort of be about y, which is sort of this sort of buckling mode right here, which is sort of like coming into and out of the z direction in this way. Okay, so if you're going to buckle about the z-axis, you're fixed pinned. And if you're going to buckle about the y-axis, in this case here, you'll actually be fixed. Right? And that's because there's no pin to allow rotation about this like y direction. Right? We see that the way that this thing is slotted into this pin, yeah, okay, it can pivot sort of around this general joint here, but it doesn't have that same ability to sort of like rotate in this about this y-axis. It's like fixed in between this particular boundary here. So we have these different boundary conditions, and we know from class that these different boundary conditions manifest themselves in that buckling equation through what's known as the effective length. So just to remind you, if you have a situation that's fixed pinned, you're going to have an effective length LEFF, which is 0.7 times L. And that's going to be useful in our buckling analysis a little bit later. If you're fixed, which is what we have here about the y-axis, you're going to have an effective length, which is 1/2 L. Okay. Now, one thing you also have to consider is the area moment of inertia of this particular cross-section also plays a factor. And so when we look at what our general buckling equation is, remember that is something like pi squared EI on L prime squared, or L effective squared. We have this area moment inertia that comes into play, and we have the effective length that comes into play. In this particular example, we have to sort of consider buckling for both of these possible situations, either buckling about Z, which would be kind of like this sort of orientation here, or by buckling about Y, which is kind of like coming into and out of the plane, kind of here like this. All right, so let's go through this, and hopefully we can we can see what this is going to look like. Okay. Last thing I want to take a note here for this particular problem statement is that we're asked for a factor of safety of 2 with regards to buckling. So more or less, we're just going to calculate what load is required and then divide by 2. Right. Okay, so let's get on with it, and let's show what the critical load for buckling is for buckling about either one of these axes. Okay. So let's start with the z-axis. And the first thing I want to do here, I'm actually going to create an image of my cross-section. Right? So we're told that this is a 2-inch by 1-inch cross-section, but I want to be very careful about putting my axes in properly. So here, this is sort of our 1-inch dimension, and this side is like our 2-inch dimension. And if we go back up to our image and sort of look at what this is actually going to look like, if I think about looking down the x-axis, I'm going to have z to the left and y up. So if I wanted some coordinates in here, z to the left, y up. Okay. So now going through this, you can see at this point that the area moments of inertia in about each one of these two axes is going to be different. So if we're thinking about the area moment of inertia about the y-axis, we'd have something like 1/12 the height times the base cubed. So here this will be 2 inches times 1 inch cubed. Okay, so if you work through this, you should end up with, I'll just keep it in fraction form because it's easy. 1/6 inches to the 4th. Okay, hopefully we can see that multiplication pretty easily. Now, similarly, for z, you can go through the same concept. 1/12 now base times height cubed. So this will be 1 inch times the height, just 2 inches cubed. In this case, we're going to have 8 on 12, or 2/3 inches to the 4th. All right, you can write in decimal form if you want, but when it's this easy for fractions, I'll just keep it in the fraction form. Okay. All right, so these will kind of come in to play later. Specifically, we're going to start with the z direction. So let's now dive in on that z direction. And so remember our boundary are what is fixed pinned, which again means that my effective length is 0.7 L. All right. Go back up to my figure. I'll take a look at what the length is. Here we're told that the length is 10 feet, but most of my calculations in this particular problem have inches that sort of float around. When I think about, area moment of inertia, this is in inches to the 4th. When I think about the elastic modulus, this is going to be something like MSI or KSI, that's kips per square inch. So I want to convert that 10 feet into inches. So if I do that here, it's going to be something like 7 feet for my effective length, and if I convert to inches, 84 inches. All right, so I'll use that in my calculations. All right, so on we go. So my critical buckling load that we derived in class, I'll put a z here to denote that this would be the required load to buckle about the z-axis. Here's going to be pi squared EI on L squared. So we're going to write that here as pi squared elastic modulus. And now we'll say this is IZ that we care about for buckling about the z-axis over the effective length about z squared. All right, so we can start putting some numbers into this now. So here we have pi squared times the elastic modulus. I can go all the way back up to my problem statement for that. Here I see the elastic modulus is 29 MSI, or 29,000 KSI. I'll just write this as 29 MSI. Multiplied by area moment of inertia about z. So I just remind myself that's up here, this 2/3 inches to the 4th. All over my effective length for buckling about this z direction, which I calculated before as 84 inches. And don't forget, we got to square this guy. Okay, So my critical buckling load for buckling about Z, after you just kind of punch the numbers here into your calculator, you'll get 27 kip. Okay, that's what you would calculate directly. If you wanted to think about using your factor of safety right here, right now, okay, fine. So we'll say with factor of safety equal to 2, that we would report that, all right, critical buckling load about Z with a factor of safety of 2 included is going to be 13.5 kip. Okay, and this would be the required load to buckle this column about the Z axis. So again, remember that is buckling about this general axis. So sort of thinking about curving about that axis. So this sort of buckling mode here. Actually, if we're going into that fixed end, it's probably a little bit more like this. It's probably a little bit more accurate representation. So that's the Z direction. Now let's take a look at the load that would be required to buckle this thing about the Y axis. So all right. Here again, we have a different boundary condition, and you can go back up and remind yourself what that boundary is, but here for the Y direction, the boundary is fixed. That means that your effective length is whatever the length is actually given for the column divided by 2. Or here, this is going to be 5 feet. Or if we convert to inches, will be 60 inches. Okay. So we're straight away just ready to calculate what's the critical buckling load for buckling about Y. So here, the critical buckling load for buckling about Y, something like pi squared E now IY, because again, we're buckling about Y and we care about the area moment of inertia about the Y axis at this point. Now over the effective length in the Y direction squared. Okay, so we end up here with pi squared, elastic modulus 29 MSI, times area moment of inertia about Y, remind you is 1/6, all the way back up here, that's this guy, 1/6 inches to the 4th. All divided by my effective length for buckling about the Y axis, here's 60 inches squared. Okay. Work this out. You will determine that the critical buckling load for buckling this column about the Y direction is going to be 13.3 kips. And that is without any factor of safety. So if we consider now the factor of safety, we normalize the 13.3 by 2, and you'll calculate the critical buckling load for failure about the Y direction. Here is going to be 6.65 kip. And this is your answer. And I like this particular problem because you really have to consider different buckling orientations, different boundary conditions, understanding how the effective length plays into this, understanding how the area moment of inertia in the various directions sort of alters the calculation, and away you go. So sort of in final sort of statement, we might say column buckles about Y-axis with factor of safety equal to 2 at load of 6.65 kip. So that would sort of give your audience, whoever you're reporting this to, sort of a nice rounding out of the problem. So let's just show one more time what that buckling mode might look like. So here for buckling about Y, that would be buckling about this general axis. So I think about bending about that particular axis or failing about that axis. My shape, if I sort of draw this correctly for the elastic curve, it's going to, zero slope at a fixed boundary. It's going to balloon out a little bit, and again, zero slope at a fixed boundary. So ultimately, my shape is going to look like this when buckling occurs, and it's going to kind of bow out in that general z direction. This is actually a buckling about the y-axis because you can sort of think of it buckling around that vertical y-axis. Okay, so that'll conclude this example problem and pretty much conclude the course. Like I said in class, I hope you enjoyed the course. Like I said, I really, when I was your age, this class really got me to look at the world in a different way. When you look at an I-beam, understand why it's shaped that way and those sorts of things. You see that all the time. So maybe you're looking at the world differently now and you can never go back. All right. Hope to see you guys in future class offerings. Definitely see you for the final. And let me know if you have any questions. I'll hold my normal office hours next week. Take care.